Let's look at an interesting problem, robot room cleaner. Nowadays, the robot room cleaner is moving around the house and do the housekeeping. And those gadgets can move forward, turn left, turn right, and detect obstacles in front of them and move around those obstacles and continue the work. This problem is to write a brain for those robots. Here, let's take a look at the hardware. The manufacturers usually provide the APIs for us. Here is the typical interface. It supports 4 actions. Forward action, the robot uses a sensor to detect any objects in front of it. If there is an object, the robot will remain in the same position, otherwise it moves forward. The robot is able to turn 90 degrees left or 90 degrees right. The robot have a procedure to clean the floor underneath, either use a mop or use a brush, depending on the manufacturer's specifications. Once the manufacturer exposes the interface to us, our Java program or C program is able to call that function in order to have the hardware to perform the corresponding action. So now we have the hardware. What left is write a brain for the robot. Here we first model the room floor as a 2D grid. Each grid cell can have 2 conditions. Condition 1, the cell is blocked, the robot cannot move into it. The other condition is 0, the floor is open, the robot can move into it and clean the floor. This is a program. Actually, this room floor visiting is a classic graph DFS traversal. We can DFS traversal this 2D grid and visit all the connected open nodes. Once the DFS call returns, we just visited all the nodes we can possibly reach. So first, let's forget about the robot. Let's write the standard DFS graph traversal. Here is a code. We need a visited hash set to remember the cells we have already visited. And this point object is an inner class. It have a position x and y. Equals are overwritten because only when the x and y are exactly the same we know they are in the same position. Don't forget to override the hash code. The next thing is we are given the start position, for example 0, 1. Then we do the DFS. In the DFS, we first add the current position as visited. Then we recursively visit all the 4 neighbors. At each cell, there are 4 neighbors. They are at the top, right, bottom, and left. This technique allows us to visit all of them. First, this row mask means we -1 for the row and the column remain the same. That is the cell at the top. The row didn't change. We add 1 to the column. That is a cell at the right. We add 1 to the row. Column don't change. That is a cell at the bottom. This cell is a cell at the left. This iterate will visit the top, right, bottom, left in that order. Now let us take a look at a CAN move. inside this can move, if we already visited the current cell, we return false. Otherwise, we check the boundary condition. If column or row out of boundary, we return false. Otherwise, we check if the current cell can be visited. If there's no obstacle, we just visit it. So this DFS call, recursive call, once it returns, we go to the next neighbor, then go to the next neighbor. Then we go outside of this DFS and check the next neighbor. This is a standard DFS traversal. Now the robot part. How do we call the robot API inside this DFS function? First, when we visit a position the first time, the robot need to clean it. After that, the robot need to turn 90 degrees and visit all those 4 neighbor cells. The order doesn't matter. Each time the robot only turn 90 degrees. So this is a robot. It's first it's facing the upward, turn 90 degree, allow the robot to facing the next neighbor, then turn 90 degree, allow the robot to facing the next neighbor, turn 90 degree, allow the robot to face the next neighbor. Finally, turn 90 degree, the robot face the original direction. So this is the turn right is for. And let's check the can move. If the robot have an internal memory, if the cell, if the neighbor cell already visited, the robot don't visit again. Otherwise, the robot will use a sensor to detect if there's an obstacle in front. So if we are using robot, we call this line instead of those lines. And the effect is the same. If we are out of boundary, right, the robot is just facing a wall. The sensor will detect the wall and return false. So in that condition, if we are hitting a wall, the robot return forward will return false. And when the cell is 0, the robot sensor will detect nothing. It will move into that cell. If there is a blocker, the sensor will detect it and return false. So the can move just move it into the next neighbor or remain the same. If after the can move, the robot is still at the same position, the robot turn 90 degrees right in order to check the next neighbor. And after the DFS recursive call function returns, the robot needs to move back to the previous cell and check the next neighbor. So this is a move back. Before the DFS function call returns, the robot needs to perform a move back. The move back, turn right, means the robot turn around, then it forward, that move it back to the previous cell, but the robot is not facing the next neighbor. Only when it turn left, it will face the next neighbor. So let's take a look at this this graph. First, the robot can move the robot into the next neighbor. Then the robot check. This is a wall, so the robot turn right. This is an obstacle, so the robot turn right. This is visited, so the robot turn right. Again, this is an obstacle, so the robot turn right, and the robot just checked all the 4 neighbors. None of them the robot can move in, so at this point the robot finished the DFS call. It need to go out. Before it go out, it calls a move back, which is turn right, forward, turn left. Let's see what it does. Turn right, to turn right. Just makes the robot turn around. Then the robot move forward, which move it back to the previous cell. Then the robot turn left. That is the next neighbor it need to visit. So exactly what we want. Now the DFS function returns. We check the next neighbor in this loop. The next neighbor, we check the can move, which is true can move. So the robot, after this can move call, the robot move into this cell and start to recursively call this DFS again. And at the end, the robot will visit all the corners in this room. And the time complexity is O 4 power n. N is the open cells in this graph, because at each open cell the robot need to check 4 directions. And the memory complexity is On, because that is the depth of the quarter stack. And basically this is how the commercial robot room cleaner works. We just examined the robot's brain. Hopefully this is both interesting and useful.